Hello, everyone. So it's a great pleasure to have here today Andrea Wei Coladangelo. So Andrea is a postdoctoral scholar at the Simons Institute at UC Berkeley, where he's hosted by Umesh Vazirani, and he has received prior to that his PhD from Caltech, and then even earlier than that, he studied mathematics in Oxford. And he has worked by now on a variety of topics around quantum computation and information. And on the way, he also won several awards, including the Best Student Paper Prize at QIP, which is the main quantum information and computing venue. He also generally cares about education in the quantum computing space. He has in fact founded QBraid, which is a cloud-based platform for learning quantum computing and developing quantum algorithms. So you might, if you get a chance, ask him about that. And today he's going to tell us about his recent work showing how quantum computers are going to change the landscape of cryptography in several ways. And so as usual, please ask any clarifying questions in the chat at any time. Maybe keep the longer questions for the end. Also, Andrea has hinted at the fact that if you find a good point to interrupt him, you can also try to just ask your question, so he enjoys some interaction. But if you hesitate to do that, feel free to write in the chat, and then I will interrupt Andrea gently. And so without further ado, so I'll leave the virtual stage to Andrea.
Thank you for the kind introduction. Okay, so I'll get started. So, you know, it's probably an understatement to say that there is broad excitement for quantum computing's impact in many areas of computation, from speeding up calculations in chemistry and physics to optimization problems and cryptography. So one thing that many of you know is that currently quantum experiments are on the verge of providing real impactful applications for quantum chemistry or quantum simulation. But what you might not know is that quantum information has been used to implement quantum cryptography protocols in practice for several years already. So cryptography is one area where quantum computing is already a reality and where quantum advantage is very clear-cut. And this area will be the focus of today's talk. And so what does the intersection of quantum computation and cryptography look like? Well, on the one hand, quantum computers threaten the foundations of most of today's encryption, since they can efficiently solve problems like factoring and discrete log. And this has motivated a shift towards what is referred to as post-quantum cryptography. So this term refers to classical cryptography that is based on assumptions that are thought to be secure even against quantum computers. And the primary example of this is lattice-based cryptography. And this shift is very much ongoing. In fact, the last competition by NIST to select the new cryptographic standards has focused on post-quantum proposals. And then on the other hand, on the positive side, we know that quantum communication, so the exchange of qubits, compensates partly for what was lost. In fact, it allows us to realize key distribution with unprecedented levels of security, where key distribution is just a protocol for two parties to agree on a secret key. And this research direction is what is traditionally referred to as quantum crypto. And it has focused, not only in theory, but also in experiments on realizing key distribution. And we indeed have experimental realizations that allow parties to exchange keys securely at distances of over 1,000 kilometers. And now the security that is achieved in this case only relies on the fact that the laws of quantum mechanics are true. So security is actually information theoretic. It holds even against computationally unbounded adversaries. And this is in contrast with classical crypto, where security is typically based on computational hardness assumptions. So in other words, security relies on the assumption that a certain computational problem is intractable to solve. And then a protocol, as a consequence, is secure only against computationally bounded adversaries. Okay, however, I would argue that this kind of quantum advantage is only slight in practice. In fact, almost all of the cryptography that we use today settles for security against computationally bounded adversaries. And this is, completely fine for virtually all practical purposes. So it is unclear if the upgrade in security sort of justifies the overhead in quantum technology. And moreover, this type of advantage is anyways essentially restricted to key distribution, and this is due to a theoretical barrier. And so for the longest time, since the early days of quantum information, this here has been the picture of the intersection of quantum computation and cryptography. And in this talk, I'll offer a different perspective on this intersection. And so classical cryptography is actually so much more than just encryption. You know, in the last 3 decades, our view of cryptography has evolved far beyond encryption. We live now in a world that is increasingly connected, where we rely on complex protocols to ensure that our systems behave as intended, even in the presence of malicious adversaries. And so we have developed many new tools and applications like digital signatures, zero-knowledge proofs, multi-party protocols, and many more. And so what I am excited about is understanding the interplay between quantum information, so quantum capabilities, and this modern view of classical cryptography. So what can we achieve with quantum capabilities when we settle for security against computationally bounded adversaries? And in doing so, we open the door sort of to the beautiful theory that has been developed by classical cryptographers over the past decades. And so what does this new intersection look like? So this intersection is actually really rich, not only with applications, but also with very interesting fundamental questions. And we're really only scratching the surface. So here are some examples of the directions that are being explored. So one exciting direction is to realize cryptographic tasks that are entirely beyond what we can hope to realize classically. And there are several examples of tasks that are, simply impossible to realize classically, even under computational assumptions, but they are possible quantumly. And these applications often leverage what is known as the no-cloning principle of quantum mechanics, which says that quantum states cannot be generically copied. And I'll give you an example of this shortly. Now, another natural direction that falls under this umbrella is to realize existing cryptographic tasks that we care about, but from weaker cryptographic assumptions than what is known classically. And so to provide some context, one of the overarching goals of cryptography is to prove reductions between different tasks. So to understand which tasks imply which others. So this research direction here is about understanding how the landscape of cryptographic tasks changes in the presence of quantum information. And I will also show an example of this in a moment. And then a third direction that is intimately connected to the other two is to understand how the presence of quantum information affects existing security proofs and definitions. So it turns out that making our current crypto systems secure against quantum computers actually takes more than just replacing a quantumly broken assumption like factoring with a quantum secure one. But in several cases, it's the security reduction itself that relies on the fact that the adversaries are classical in a very fundamental way. And so one has to rethink such proofs in the presence of quantum algorithms. And of course, in many cases, even coming up with the right definitions of classical concepts in the quantum setting is something that can be very subtle. And so my work has made contributions to all of these directions. And in this talk, I will start by introducing first the no-cloning principle, which is probably the main ingredient in quantum cryptography. And I will then describe at a very high level a couple of examples of results in these directions here on the left. And then I will take a deeper dive into one particular result, which is about how to protect against coercion in online elections, which is one of the many timely questions that cryptographers think about today. And this work shows that we can deal with coercion in a fundamentally new way using quantum computation. And then I'll conclude with a discussion of what I think are the important questions ahead. Okay, so before diving into this, I just want to zoom out for a moment and tell you why I think we should pursue these directions in the first place. So in particular, why study cryptography and quantum computation together? So my main motivation is that cryptography is a powerful lens through which we can understand quantum computation. And our exploration of this interplay is only at the beginning, but it's fair to say it has already produced deep ideas in quantum computation. And I think this is not surprising because cryptography brings to the table two of the most influential ideas in theoretical computer science, namely interaction and computational hardness. And then conversely, quantum computation is bringing along a paradigm shift in cryptography. So firstly, it unlocks cryptographic tasks that were otherwise impossible to realize. And secondly, our world is quantum. So to me, understanding cryptography means understanding it in the presence of quantum computation. And there's this whole new territory that is only revealed when you consider the two together, that is essentially waiting to be mapped out. Okay, so then how can quantum information be useful for cryptography? So one of the main ingredients is what is known as the no cloning principle. So this simply says that quantum states cannot be copied in general. So more precisely, there is no universal procedure that takes as input an arbitrary unknown quantum state and outputs two identical copies of it. Now, in a cryptographic setting, the no cloning principle is very useful because it restricts the types of strategies that are available to an attacker. So imagine the following simple scenario where Alice and Bob are trying to share a secret key by communicating over a public channel. Well, classically, any communication between Alice and Bob can be intercepted by an eavesdropper Eve without disturbing the communication. Now, quantumly, Alice and Bob can exchange qubits. So unlike a bit, which can be only 0 or 1, you should think of a qubit as a two-dimensional vector. So two continuous degrees of freedom instead of two discrete options. So a vector that can point in any direction. Now, Eve could again try to read the communication, but this time the no cloning principle says that Eve cannot simply read or copy out the state of the qubit if she doesn't have any prior information about it. In fact, in general, any attempt that Eve makes at extracting some information will disturb the state on its way from Alice to Bob. So for example, Eve could attempt to extract some classical information by making a measurement. And a measurement is like a question. So you're asking the qubit, are you vertical or horizontal? And the same question can be asked, with respect to any other basis. And now the laws of quantum mechanics say that here Eve will get a uniformly random answer, either horizontal or vertical. And as a result, the state of the qubit will collapse accordingly. So measuring in general disturbs the state of the qubit. And you can imagine that if Alice and Bob come up with a clever protocol, they could take advantage of this. They could leverage this idea to detect any eavesdropping attempt. So either they would detect that Eve eavesdropped, or they would be satisfied that Eve has learned nothing. So this is the essence here. And so what more can we do with the no cloning principle? Okay, so one fascinating example of a task that is entirely beyond what we can do classically is called copy protection of software. So what is this? So a copy protection algorithm takes as input a classical program, a piece of code, and outputs a functionally equivalent program that cannot be copied. Okay, so you start with a program P on the left that you want to copy protect, and you obtain a new program with the same functionality, but with the property that it cannot be copied or pirated. And now, of course, this task is impossible classically, since any program, however you write it, is ultimately just a string of bits, right, which can always be copied. And so the idea to circumvent this is to leverage the no cloning theorem and encode the original program in a quantum state. Okay, then using a quantum computer, anyone in possession of this quantum state can evaluate the original program on any input they want. And the intuition for security would be that by the no cloning principle, the state, or in fact, the functionality of the original program cannot be copied. And so what is the difficulty in achieving something like this? Doesn't the no cloning principle sort of trivially give us what we want? Well, not quite. The no cloning principle only says that it is impossible to copy an arbitrary unknown quantum state, but states that have a particular structure may be very easy to copy. And so the crux in designing a copy protection scheme is to encode the classical program in a quantum state such that there is enough structure that the desired program can be evaluated, but not so much structure that the state can be copied. And so what we really need is some sort of a cryptographic version of the no cloning principle. Now, the problem of copy protection was proposed by Aronson in 2009, and despite many candidate constructions since then, a provably secure one has been missing. So we didn't know how to copy protect any non-trivial class of programs. And in a recent work, we give the first provably secure constructions of copy protection for certain small classes of programs under plausible computational assumptions. And so this was sort of an example of a task that is entirely beyond what we can do classically. But I just want to share, one other example in which quantum information helps realizing an existing task that we care about, but from weaker assumption than what we know how to do classically. So in this example, we consider the task of multi-party computation, which is a very general cryptographic task. It's well studied. In some sense, it is the ultimate cryptographic task in terms of expressiveness. It allows a set of mutually distrustful parties to compute any joint function over their private inputs. And they will do this by interacting with each other, but crucially, they want to do this without revealing anything more to each other than what is strictly necessary. And so as an example, think of a group of hospitals that want to sort of jointly compute or train a predictor to diagnose cancer using their patients' data, but they don't want to openly reveal this data to each other. And so multi-party computation is how they can do it. And what we show is that using quantum communication, this task can be built from essentially the minimal cryptographic assumption that is known to be useful to cryptography, which is the existence of one-way functions. So these are functions that are easy to compute, but hard to invert on average. And this assumption is minimal in the sense that virtually all other cryptographic tasks imply one-way functions. And our results shows actually a stark contrast with the classical setting, where multi-party computation provably cannot be realized from just the existence of one-way functions if these are used in a black box way. Okay, good. So now that I've shown you a couple of examples that hopefully kind of give you a bit of the flavor of this research area, I'm sort of ready to move to the main part of the talk, where I'll take a deeper dive into one particular work. And I decided to focus on this because while the examples that I just described, they fall quite clearly in one of the three directions here. This work here, in some sense, touches upon all of the three. And this work is joined with Shafi Goldwasser and Umesh Vazirani. So let me start with the takeaways. So the first takeaway is that we show how quantum computation, together with cryptography, can be leveraged to protect against coercion, for example, in online elections, in a way that is fundamentally impossible classically. The second takeaway is that the quantum advantage in this work does not actually involve quantum communication. So based on our earlier examples, you may have expected that quantum advantage in cryptography comes from quantum communication, from the ability to detect an eavesdropper that is tampering with the qubits that are being exchanged, or from sending someone a quantum state that encodes a program, like in the copy protection example. But instead, we show that in our work, quantum advantage really comes from local quantum computation. And then the third takeaway, perhaps the most conceptually interesting, is that we provide a new perspective on the notion of proofs in a quantum world. Okay, so the topic of protecting against coercion, for example, in online elections, has been studied by classical cryptographers through a notion called deniable encryption. So a deniable encryption scheme is a public key encryption scheme with one additional property, which captures the following scenario. So consider a sender who produces a ciphertext C. Now, in general, this ciphertext is obtained by running a probabilistic encryption algorithm, ENC, on input the public key and a message M. right? Or equivalently, we can think of also of ENC as a deterministic algorithm, which additionally takes as input some randomness, some coin flips. Now imagine that an attacker intercepts the ciphertext and approaches the sender and says, show me your encrypted message. Right? In other words, the attacker is forcing the sender to reveal their message and the randomness used. And of course, by running encryption forward, the attacker would be able to check that what is being reported is consistent with the intercepted ciphertext. And now we say that the encryption scheme is deniable if there is a way for the sender to deny. So meaning if there is a way for the sender to come up with fake randomness, R prime, which is consistent with some other message M prime of her choice. So in other words, if there is a way for the sender to come up with a different explanation of the ciphertext, which will still satisfy the attacker. And the typical story used to explain deniable encryption is the following. Imagine an online election where citizens encrypt their votes, say for candidate A or candidate B. And then the government samples a secret key and a public key. It keeps the secret key for itself, which it will use to decrypt the votes. And then on the day of the election, it announces the public key to everyone. And then each citizen encrypts their votes and sends it to the government over a public channel. And an attacker can intercept this message, approach the sender after the fact, and force the sender to reveal their vote. And so deniable encryption provides a way to deny, and so to defend against such a coercion attack. And now our first result is that deniable encryption can be realized from weaker cryptographic assumptions in a quantum world than we know how to do classically. In particular, we show that it can be realized assuming the quantum hardness of the learning with errors problem, LWE, which is one of the main lattice-based candidates for post-quantum security. And in contrast, classically, we only know how to realize deniable encryption from stronger assumptions like obfuscation. Okay, and now as we were trying to understand the nature of this quantum advantage, which I'll explain to you shortly, we realized that our ideas could actually be employed to obtain a fundamentally stronger form of protection against coercion, which is impossible to achieve classically. And so I find this new property that I'm about to describe quite interesting, even besides the potential application to this scenario of coercion, because it highlights what I think is a new fundamental perspective on proofs. Okay, so the shortcoming of deniable encryption is that it only deals with coercion after the fact, meaning that the attacker approaches the voter after they have sent their encrypted vote. However, in practice, if someone intends to coerce you, they would most likely do it before the fact. So the following is instead the scenario that is of even greater concern for online elections. So the attacker approaches the sender before she sends her ciphertext and prescribes to her what randomness she should use later. So the attacker says, vote for candidate A using randomness R. And then on election day, the public key is announced. The voter encrypts her vote using the randomness R prescribed by the attacker, and the attacker can later intercept the ciphertext and verify that it is consistent with an encryption of A using the prescribed randomness. And if you think about it for a moment, you will realize that this attack is actually impossible to prevent. Notice in particular that the attacker doesn't even need to know the public key, which is announced only later on election day. Yet the attacker can still prescribe the randomness beforehand. And so coercion before the fact in this setting is impossible to prevent classically. And in stark contrast, we show that coercion before the fact can be prevented by using quantum computation, and this is our main result. And so how is the quantum setting different? Okay, so we will consider the setting where encryption is a quantum algorithm, So the citizen encrypts by running a quantum computation on her local quantum computer. So this here on the right is a quantum computer, but the output of the computation, the ciphertext, is still classical. Okay, so everything is identical, except encryption is a quantum algorithm. Well, then one crucial difference is the following. Okay, while a classical probabilistic algorithm can always be thought of as a deterministic algorithm together with some input randomness, for a quantum algorithm, the concept of input randomness is not well defined, in the sense that randomness could be intrinsically the result of a measurement. Okay, right? So as we saw earlier, when you make a measurement, you get a random outcome and your state collapses. And so this outcome in general cannot be post-selected for. It cannot be fixed beforehand. And so the following notion of protection against coercion becomes in principle possible. So it's in principle possible that there is an encryption scheme such that it is intractable to produce both a valid encryption C of some message M, as well as a proof that C is a valid encryption of M. And when I say valid encryption here, I mean that it is in the support of the distribution of encryptions of M. That's what I mean by valid encryption. I'm also being a bit informal for the moment with the term proof here. I'll be more precise shortly. But what I mean is a proof in the NP sense for now. Okay, so importantly, here a proof is with respect to someone who does not have the secret key. So of course, the government can always use the secret key to decrypt and be convinced that the ciphertext is an encryption of M. Okay, but here the proof should be a certificate that convinces the attacker that the ciphertext is a valid encryption of M. So this is what we're asking shouldn't exist. Are there any, let me stop for questions maybe. Are there any questions that I can answer?
Oh yeah, so Rachel is asking if the ciphertext is meant to be classical.
Yeah, the ciphertext is classical here. Okay, so then the first observation is that, classically this property here is impossible to achieve. So this is because one can always run the classical encryption algorithm, sampling some input randomness uniformly, and then the randomness itself is a proof that the ciphertext is a valid encryption of M. But in the quantum setting, it's in principle possible that there is some quantum encryption algorithm that on input a public key and a message produces a valid ciphertext 100% of the times. However, it is unable to simultaneously produce a proof that the ciphertext is valid. So this would be protection against coercion in a very strong sense. It says that there is no point for an attacker to approach a voter because the voter just cannot prove to them or to themselves who they voted for, even if they wanted to. Moreover, there isn't even a way for an attacker to prescribe to the voter how to encrypt before the fact in a way that it can later verify, since this would also violate this property here. It would imply that there is some way to encrypt and to provide a proof later.
Sorry.
Yeah.
So the question is like, can the attacker hand to the voter a ciphertext C and say, please use this ciphertext C instead? So is that something that's possible?
Yeah.
Here? Yeah.
Good question. So in our setting, the coercion happens before the public key is announced. So the public key is only announced on election day. So the attacker has all the time in the world before election day to coerce, but it doesn't know the public key, so it cannot hand a ciphertext beforehand. If the public key was known to the attacker, then there's really nothing you can do precisely because of this reason. You can just the attacker can just find a ciphertext and give it to the voter. So that scenario is absolutely in any physical model that's impossible to defend against. Here, the public key is announced on election day. We give the attacker all the time in the world to do anything they want before, to prescribe anything they want before. Yeah.
Thanks.
Ultimately, our scheme satisfies this property here, assuming that the learning with errors problem is hard for quantum computers. Okay, so our proof of security is also in an idealized model called the random oracle model. This caveat, it may be meaningful to cryptographers, but it's somewhat immaterial to the discussion here. Okay, so now in the next part of the talk, I will zoom in and sort of abstract the crucial question here, which is, can there really be a computational task that can be accomplished efficiently, but such that it is not possible to efficiently provide a proof that it has been accomplished correctly? Okay, and I'll be a bit more precise in a moment, but before thinking deeper about this question, I just want to remark that proofs have been at the center of the stage in complexity and cryptography in the last 30, 40 years. We have come up with proofs that have all sorts of incredible properties. We have thought of interactive proofs, probabilistically checkable proofs, zero knowledge proofs, succinct proofs, even proofs that are hard to pronounce, like SNARKs. But what if instead we wish to not be able to prove? And the setting of coercion that I just described is an example of a setting where such a property may be desirable. So if you're unable to prove who you voted for, you can't really sell your vote. You can't be coerced into revealing who you voted for. And I think we're only at the beginning of exploring proofs under this new light. So let me be a bit more precise about this question here. So first, what do I mean by a computational task? So I mean the following. So on input some string x, the task is to output a string y such that y is in some set R of x. So this is a relation problem, basically. And now, what do I mean by a proof? I mean a proof in the NP sense, or QMA sense, if you allow the proof to be a quantum state. So W is a proof for some xy if there is an efficient algorithm verify, such that verify outputs accept on inputs x, y, and w. And moreover, verify only accepts correct solutions, meaning it only ever accepts pairs xy such that y is a correct answer. So in other words, W should be a certificate that the solution y is correct. Okay, then our intuition should tell us that a task satisfying this property up here should not exist. The reason is that a classical computation has a transcript. Okay, you can think of a classical computation as a sequence of logical gates that you apply to some wires, and we take it for granted that it is possible to copy out on a piece of paper the values on each of the wires as we go through the computation. And so if we have an efficient classical device that we know accomplishes a certain task correctly, then the transcript of the computation itself can serve as a proof of correctness. And so our hands are tied. But now quantum computation is different. So a quantum computation does not have a transcript, or at least not one in the same sense as for classical computations. Rather, you should think of a quantum computation as starting with an initial quantum state, say psi 0, and then each quantum gate evolves or transforms the state into a different one. And so in general, once you apply a quantum gate, you have a new state. You no longer have the original state. So in this sense, a quantum state is closer to a physical object. Okay, and then as the final step of the computation, the quantum computer may perform a measurement of the current state or part of it and extract a classical output, and maybe also have some leftover quantum state on the registers that have not been measured. And so, of course, by the no cloning principle, in general, any naive attempt to copy wouldn't work, to copy out all of these intermediate states as the computation goes along. Any attempt to copy or measure in general disturbs the computation. So it seems that it is in principle possible that the answer to the question up here is actually yes. There in principle could be such a computational task. And our main result is that we identify such a computational task and show that it satisfies this property. And this is assuming some plausible cryptographic assumptions. And this computational task was previously considered by Brakersky and co-authors in a different context, in a work that I actually consider emblematic of this thread of leveraging cryptography in conjunction with quantum computation. And so in our work, we take a deeper look at this computational task, and our main leap forward is establishing that it satisfies this new property here, which we formalized. Are there any questions? Actually, maybe it's a good point to take a question.
I think it looks good. So
okay, sounds good. So what is it that makes this property difficult to establish? Well, there is quite some gap between this being in principle possible and finding and establishing that a task provably satisfies this property. And the main difficulty intuitively is that we may have in mind one particular quantum algorithm that solves the computational task efficiently. And perhaps for this particular algorithm, it is somehow possible to argue that after having produced a Y, the leftover internal quantum state is not really useful anymore for producing a proof. Okay, however, what we want to argue is that all quantum algorithms that are successful at the task cannot also be producing a proof. So our argument will have to at some point characterize the structure of strategies that are successful at the task, and hopefully that structure is sufficient to argue that you cannot also be producing a proof. So I'll now describe this computational task, or slight simplification of it, that carries all of the essence. I'll do my best to provide some intuition. But the description of the task should be quite simple to follow, hopefully. So consider a family of efficiently computable functions f indexed by a subscript k, where each function here is 2 to 1. So the picture is the following. Given a point x0 in the domain, one can efficiently find the image y under fk. And each point x0 also has a sibling x1, which also gets mapped to y under fk. Now, moreover, the function should be collision resistant. What this means is that it is hard to find a pair of inputs that map to the same output. So we call this a collision. Now, such a cryptographic function f can be constructed, for example, from the learning with errors assumption. And so then the computational task is the following. On input k, which specifies a function from the family, you're asked to output an image y, this should be in the range of fk, and a bit z, where informally z is what in cryptography would be known as a hardcore bit. So this is some bit of information that depends on both preimages of y. So in particular, in this case, it will depend on the XOR of the two preimages, x0 and x1. So this is called a hardcore bit because it is meant to be computationally unpredictable to any adversary who is given only y. And to be precise, although this is not important, in our case, it will be the inner product of the XOR of x0 and x1 with some non-zero string r, which can be chosen by the algorithm. And now, intuitively, we wouldn't in general expect a classical algorithm to be able to output such a hardcore bit. And the intuition being that you would expect that the only way for a classical algorithm to obtain information about the XOR of the two preimages would be to have obtained information about both of these preimages separately at some point during the computation. Right? And this seems to be a little bit at odds with the collision resistance property. And yet it turns out that there is actually a very simple way for a quantum algorithm to obtain such a hardcore bit. And indeed, the quantum algorithm will at some point during its computation obtain information about both x0 and x1, but this will be in the form of a superposition of the two. And now this superposition, it could be measured right away, for example, and this would give us one of the two preimages uniformly at random and would collapse the state to that preimage. But this is not very interesting since all in all, this is something that a classical algorithm could have also accomplished, starting first from x and then computing its image f of x. Instead, the quantum magic is that there is a way to make the x0 and x1 branches interfere to obtain a bit of information that depends on both. And this is precisely a hardcore bit. And so this interference part is maybe something that you can take on faith for this talk, I guess. Okay, but now you may be wondering, surely if there's a way to obtain this uniform superposition over the preimages of y, this x0 plus x1, then I can run whatever quantum computation I did to get there twice, right? I run it twice with the same randomness and obtain the same state twice. At that point, I have two copies of this superposition. I can measure both, and it's quite likely that I'll get distinct preimages. Well, the issue with this, like we mentioned earlier, is that the randomness in the outcome of a quantum algorithm can truly be due to the measurements, and it's not something that can be post-selected for. So in the case of this particular quantum algorithm, the image y is uniformly random, and there are exponentially many y's. So each of them is exponentially unlikely. So you should think of each run of the quantum algorithm as sort of a lightning strike. The lightning never strikes the same output twice, or almost never does. So for instance, if we were to run the same quantum computation again, we would most likely obtain different triples each time. Okay, so I've sort of told you that there is this simple quantum algorithm that can successfully produce a hardcore bit. But why is it hard to produce a hardcore bit and also prove of its validity? Okay, and the intuition is that the only efficient way to obtain a hardcore bit is to run this particular quantum process that I described. So to obtain a uniformly random image y and a superposition over its preimages, and then have the two branches, the x0 and x1 branches, interfere delicately in just the right way so that no information is left behind to explain the validity of the hardcore bit. And so formalizing this intuition is the difficulty, and this is our main technical contribution. In particular, as I mentioned earlier, this property has to be argued with respect to all efficient quantum algorithms, not just the particular one that I described here. Good. And so, I won't have time to discuss the details here, but instead, let me move on to sort of summarizing the takeaways here.
Oh, so there's a question.
There's a question. Okay.
Yeah. So, so is this inability to prove the result you referred to earlier, when you said you had a contribution about the meaning of proof? I think so, right? But go. Yeah. So this would be something that classically we just cannot achieve. So a computational task that you can efficiently solve, but for which is also hard to prove or give a certificate that it has been solved correctly. And quantumly, such a task, we show that such a task can exist. Thanks.
And so here are the takeaways. So we show that there exists an encryption scheme with this surprising property which protects against coercion in a fundamentally new way. Our work also shows a different perspective on the no cloning principle, right? We started with the no cloning principle as a way to detect eavesdropping, and we showed in our work that the no cloning principle can help in a different way. Namely, it is at the heart of why quantum computations don't have a transcript or don't leave a trace in general. And we then combine this perspective with cryptography in order to formalize what it means to be unable to prove. Good. Okay, so now I'll move on to the last part of the talk, where I will just try to paint a picture for you of what are the future directions that I think are important at this intersection of quantum and cryptography. Now, before doing this, let me very briefly give you a bit of background of how I got to this intersection in the first place. So, the motivation behind my research has always been to understand quantum computation and quantum information better. So most of the work that I did during my PhD, in fact, most of my work to date, actually studies a central topic in quantum information theory, which is non-local games. Now, I won't be describing what these are to you here. You could ask me when we meet later, maybe. But non-local games have connections to foundational questions about entanglement and the certification of quantum devices, which is what my work has focused primarily on. They're also at the heart of the complexity of multi-prover interactive proofs with shared entanglement, so the class MIP star. And they also have connections to protocols in quantum cryptography. And so the latter connection was for me, in a way, the bridge to cryptography and what has led to today's talk. And over the last couple of years, I've slowly realized that cryptography is a surprisingly fruitful lens through which we can study quantum computation. And so looking ahead, my main motivation for studying the two together is to use cryptography to understand quantum computation better. And now, of course, conversely, as I hopefully conveyed in this talk, quantum computation also unlocks many exciting cryptographic applications. And this interplay, is very rich and open-ended. So let me give you just a few examples of future directions, which I will put in one of these two threads, but really the boundary is very fluid, as you can imagine. So one broad question here is, can quantum computation help us realize tasks that are difficult to realize classically? So just to give you one example here, obfuscation. So obfuscation is a very sought after cryptographic primitive, which in its strongest notion, virtual black box, is considered to be one of the major unsolved problems in classical cryptography. And I think it's possible that quantum information may allow us to realize obfuscation for larger classes of programs that we can classically. And this, I think, would be something quite striking. Now, another very important direction is, and also very broad, is to realize tasks that are outright impossible to realize classically. So as an example, there is an emerging area called, people refer to it as unclonable cryptography, which I touched upon at the start of the talk. And so here the goal is to leverage the no-cloning principle to realize tasks that enjoy some form of unclonability. So some examples are unclonable decryption keys or copy protection of software, which I talked about earlier. Now, copy protection is possibly the holy grail of unclonable cryptography, but here, despite the positive results, our understanding is still very limited. We essentially have some limited positive results and some impossibility results for contrived classes of programs, but we don't really know anything in between. And so one of my goals is to obtain a full picture of copy protection. Now, another very broad direction is to understand proofs in a quantum world in various contexts. So one example that is very relevant to near-term experiments is studying protocols for testing quantumness. So these are sometimes called proofs of quantumness. So protocols that allow a classical user to certify in a cryptographic sense that an untrusted device is actually quantum. So one challenge here is to make the quantum part of these protocols simple enough that it can be carried out on near-term quantum hardware. And indeed, we are quite close to experimental realizations at scales for some of these protocols. So theoretical improvements to the efficiency of these tests would be quite significant. And now, pushing the boundary in this direction, one can also think of things like proofs of quantum space. So designing protocols that not only allow a classical verifier to certify that a device is quantum, but to certify that whatever it did, it could not have done with less than, say, 50 qubits. And I think proofs of quantumness and quantum space will play an important role in the near term as a meaningful sort of operational way to certify, compare, and benchmark different quantum hardware. So this is definitely a direction that I plan to work on, and that also connects well to the work on the foundations of quantum information that I've done during my PhD. And I'll just leave one other example here in this section where cryptography has been helpful in the past. And now another direction that is in some sense complementary to this, which we're only beginning to explore, is to understand this new concept of inability to prove and its ramifications. So what computational tasks have this property and what other applications does this concept have? And then finally, of course, quantum computation also commands that we revisit our cryptographic models, our definitions, and also our security proofs. And this endeavor, to me, is not at all separate from the other directions I described, but rather it is inherent in most of these directions, and the techniques often overlap. And I'll just leave one example here of the type of problem that still eludes us. And I guess I just have one concluding message, which is, the quantum computation is a field that has many facets to it. So cryptography is by no means the only lens through which we should study it, but I think that it is one that has already revealed and will reveal a lot of richness in the future. Thank you.
All right, so thank you. So we have a few minutes for questions. So while other people think about it, I can also start with one. So one thing that at least wasn't clear and I didn't ask before was like, if you think about the encryption algorithm as a quantum algorithm, so can you say something about the complexity or the simplest encryption algorithm that we can build in terms of, how hard of a circuit that will be?
Oh, I see. So you're thinking of implementations on actual hardware?
Yeah, for example, if I want, how far out would it be to implement it on so the simplest possible quantum architecture? I mean, that could be a way to think.
Yeah, so I think, that it so happens that this quantum encryption algorithm that I was talking about, it is also, very similar to the algorithm that is used in the proofs of quantumness that we have so far. And so in fact, there is a plan by Google to, as a next milestone, to implement a proof of quantumness. So the issue with their previous, or issue, if you can call it that, with their previous quantum supremacy experiment is that the verification, the classical verification part is intractable. And so the advantage of this new approach is that classical verification would be efficient, and they have plans to realize this. And actually, this is a collaboration that I might also be involved with. So I think it's not, it's a bit more complicated than this random circuit sampling task, but it's also not too far out. Yeah.
Any more questions? Oh, Paul has a question. Yeah.
Sure. So in quantum cryptography, is there a natural mode where you can think about hybrid protocols between quantum agents, of whom you might have fewer of them, and classical ones? So in the election ones, it seemed that every voter had to have a quantum computer to do this. Is that correct, or is there some and is there some direction where combining the two might be helpful?
Mm-hmm. Yeah, so I think there is a direction. I guess the first that comes to mind is that, yes, in the example I gave, everyone would have to have their local quantum computer. But we do also have protocols to delegate a quantum computation to a cloud in a verifiable way, so in a trusted way. So you may not trust that the cloud has a quantum computer, but you can have a conversation with it, a classical conversation with it, and delegate a computation in a verifiable way. So in that sense, that would avoid everyone having to have, their local quantum computer if you're happy with, if you're happy with citizens delegating their computation to a cloud. But then, that may raise other sorts of issues in the context of coercion, but yeah, so that's definitely a possibility. So delegating your computation to a cloud.
Thanks.
Mm-hmm.
I think let's just thank Andrea again, and virtual hand clapping. And
thank you.
Thank you.
Thanks.